My name is Charles Stegman. I'm president of Wicomico Environmental Trust. Thank you all for coming and welcome to our town hall on what to do about DAF, both online and in this auditorium, which Warwick Community College has graciously donated for tonight's event. The purpose of tonight's meeting is to provide a community forum to discuss our views and questions regarding the handling of dissolved air flotation, or DAF, residuals. As you may know, WET has expressed views of its own on DAF storage in the past, but we are here tonight as the neutral host of this event to encourage constructive discussion of issues that are important to all of us. We will hear from two panels of speakers tonight and then take questions and comments. The first panel, scientific and technological experts, will provide a brief overview of what DAF is and how it can be handled. The panel will be moderated by Hemalotha Bhaskaran of Salisbury, a former Maryland Teacher of the Year and recipient of the Presidential Award for Excellence in Mathematics and Science Teaching. She has an educational and research background in bioremediation and environmental science. The second panel, representatives of community organizations with a variety of perspectives on DAF, will be co-moderated by the executive directors of two local organizations that have not taken positions on these issues, Lisa Wool of Nanticoke Watershed Alliance and Matt Heim of Lower Shore Land Trust. We would also like to acknowledge the attendance tonight of several of our local elected officials: Wicomico County Executive Giordano, Salisbury Mayor Taylor, Wicomico County Council members President Cannon, Merritt, Hastings, Holloway, and Wynn, and Salisbury City Council members President Dowdy and Councilwoman DeShiel. We have also included members of the press and are recording this event for PAC 14. We thank you all for your interest and engagement. It has been said, if you want to go fast, go alone, but if you want to go far, go together. We hope to go far tonight. Thank you.
Good evening. Today, I have the honor and privilege and the pleasure of introducing and moderating the session with a unique team of panelists. I'm going to start by introducing Dr. Lansing. Dr. Lansing is a professor in the Department of Environmental Science and Technology at the University of Maryland. She leads the Bioenergy and Bioprocessing Technology Lab. Her research and extension work focuses on anaerobic digestion, gasification, food waste recovery, and nutrient management. She has 20 years of experience in renewable energy research, outreach, and economic and sustainability analysis of waste to energy systems. Thank you, Dr. Lansing, for being here. Our next panelist is Dr. Cumming. He's a professor and chair of the Department of Natural Science at University of Maryland Eastern Shore, and he leads the Keystone STEM Stars program at UMES. He is also a team leader in the Center for Bioenergy Innovation, or CBI, through Oak Ridge National Laboratory, a research role where he focuses on solving complicated plant-soil interactions associated with producing sustainable biofeedstocks for the bioenergy sector. And our last panelist is Mr. Casserly. He is the Vice President of Government Relations at Bioenergy DevCo. With a degree in industrial technology, Mr. Casserly has broad experience in environmental and renewable energy and organic recycling. Bioenergy DevCo is a global leader in designing, engineering, constructing, financing, and operating advanced anaerobic digestion facilities. I take this opportunity to thank each of our panelists, and for the next 30 minutes, we're going to spend a little bit of time learning about DAF and also about some of the alternative technologies. So I'm going to start this panel discussion by asking Dr. Lansing to share with us what DAF is, and also some of the alternative technologies that are available. If you could give us a big picture overview, we'd really appreciate that. Thank you.
Thank you so much. And thank you very much for having me. I'm just going to go over a little bit on just to make sure we have a foundation of what DAF is and what are some waste technologies that could be used to process and utilize DAF. So next slide. So DAF is basically it's a byproduct of food processing. So whether we're making, fish balls, or we're making crab cakes, or we're making chicken nuggets, Frito-Lays, if we have food processing, DAF is a byproduct of that. And what we basically do and that this byproduct it contains nutrients that we can grow crops. So what we do is after we come from the chicken processing plant or the dog food processing plant, we take out the bones and the feathers and things that might be in there. That gets landfilled. And all the rest of the waste that comes out, we add a whole bunch of a coagulant. We had iron basically, and then we add air. And DAF is dissolved air flotation. So it's all the stuff that comes up. It's the proteins, the fats, the carbohydrates, and all the nutrients. And so all that stuff comes to the top, and we scrape that up, and that's the DAF. And then most of it's actually left behind. Most of it's the water that's left behind, and that goes through a wastewater treatment process and gets discharged, or we put it into evaporation ponds. So what we're talking about is really all the stuff that's coming from any sort of food processing plant that has the nutrients that we want to put back on the fields to grow more crops, instead of having those nutrients go to landfill or not be there to go back into our system. So again, it's conducted on liquid waste streams after offal removal and screening to remove solids. Next. So where do we have DAF? So this is where DAF generation is in the Delmarva. So about 64 gallons per year of DAF comes from, again, about 4.4 million pounds of chicken. Again, not all DAF is from chicken processing, but in this area, a lot of it is in the Delmarva area. And so if we look, DAF is about an NP ratio of 1.5 to 1. So that means it has, for every 1 part of phosphorus, it has 1.5 parts of nitrogen that can be used to grow crops. About 72% of the DAF is generated actually out of state, because a lot of our processing plants, we have to step over just 2 miles down the road to Virginia, or step over a few miles down the road to Delaware, where we have our processing plants. But a lot of the chickens that go into those plants to make the chicken nuggets come from Maryland. But a lot of it is actually generated outside, just a couple miles over the border. And then the DAF either goes to Maryland, goes to Virginia, go to Pennsylvania, or comes here to Maryland. And then again, DAF has actually moved from 0.8 million to 6.8 million gallons from 2020 to 2022. And a lot of that movement was based on the full implementation of the phosphorus management tool. Because as we said, it has 1.5 nitrogen to phosphorus. It has a bit of phosphorus that we need to grow crops. But if we already have too much phosphorus in that soil, we can't use DAF on that soil. And so we might be moving that to other places. And so if we look at the DAF here, so if we look at Caroline County, you can see it kind of goes up and down. And this data is from the nutrient management planning from the annual implementation reports from the Maryland Department of Agriculture. And so we see we have a lot of DAF being utilized in Wicomico County and Dorchester and Caroline County. Next. So what can we do with DAF? So there's several waste technologies that I'm just going to overview on what they are and what the process is. So there's anaerobic digestion, there's composting, there's thermochemical processing, and there's injection. So these are all processes that can do with DAF. And we actually look at the nutrient management regulations from MDA. They now say that DAF has to be either digested, composted, or injected or incorporated into the soil within within 48 hours of placement. And so that's something that is part of the regulations for nutrient management, is that we have to use one of these technologies or we have to till it into the soil. Next. So what are these technologies? So anaerobic digestion is basically anything can come here. We could have agricultural waste, food scraps, animal waste, sewage sludge, DAF. So in DC, when you flush your toilet at the University of Maryland, it goes to the DC wastewater plant. There's a big digester that runs that entire plant. So digesters are used in all different kinds of industries. And basically in that digester, microbes, kind of like the same microbes that are in your stomach that break down, you eat your broccoli and it breaks down that broccoli, and we actually produce some methane. Cows produce methane, and digesters also produce that methane. And that methane is captured as biogas. We can use it directly as heat. We can scrub out the hydrogen sulfide and use it for electricity, or we can scrub out all of the things in the biogas. It's a mixture of gases that comes out, and use it for renewable natural gas. Again, a lot of the systems that, I did a lot of work in Costa Rica and Haiti and other places, and they just used it directly for cooking. So they had 5 pigs in the background, you had your biogas, and you just turned on your stove and used it directly for cooking. So you didn't have to use propane or charcoal. But here we often use it for electricity because we're at a larger scale. And when it comes out of the digester, so what comes into the digester has to come out, kind of like what goes into our stomach has to come out. And so it doesn't actually, what it does is it transforms those nutrients. So a lot of the solids, the carbon goes into methane, and what's left over are dissolved nutrients. So when you put that liquid digestate onto the fields, it actually is really good. It actually sticks to the soil because it has a lot of ammonia, and it's actually really good for crop growth. But you can also do solid separation. So you have a solid fertilizer and a liquid portion, or you can just put it all in the field. Next one. So this is an example of a digester in Cecil County that actually puts in food waste, dairy manure, and DAF into the digester. And so from this digester, they have all the waste coming in, the DAF processing waste. They actually, by just having this digester and not having that methane from manure going into the atmosphere, they're reducing over 200 tons of CO2 per year. They're making biogas that actually powers 190 homes per year. And then they land apply and do manure injection as well. They also have a composting operation. So you can kind of mix some of these things in this farm, 3 of the technologies they're doing right there on the farm, but they're getting all of their energy. So not only do they power their own farm, but 190 homes with just the energy coming from the DAF. And it's also very pleasant. When you walk to a dairy farm, it doesn't always smell very nice. It smells lovely there because all of the odors are captured inside that digester from the DAF, the food residuals, and from the manure that actually goes onto the fields. Next slide. So you can also compost. So when we're composting, what we want to do is we want to have the right mix of water, oxygen, then we have microorganisms that help break it down, and then we have our feedstock coming in. And so if we compost DAF, we do need to either dry it out a little bit, which some of the processes do, or you need to add something that kind of absorbs some of that moisture. Because with compost, we want to keep it aerobic. So we don't want it to have too much water. And then basically it's an aerobic process. And during that, we produce CO2, heat. Hopefully we don't produce any odors if we can keep it aerobic. If we keep it not wet and don't have that anaerobic, we don't have any odors. And then that compost, again, you can do windrow composting, which is an open air composting, or we can do gore composting. So where I live in Prince George's County, I actually put my food waste on the curb. They take it down to their composting site for Prince George's County, and it goes inside of a forced air composting. So it's actually a covered compost that makes that composting process go faster than the outdoor windrow composting. So you can compost either in enclosed or in an open composting vessel. But you shouldn't have any odors if you have the right combination of water, microbes, and oxygen, and you're keeping that nice and aerated. Next slide. So there's also thermochemical processing. This is normally done on very dry material, okay? But we can thermochemical process. And so when you say what is thermochemical processing, you can just dry something. You can do pyrolysis, which is the absence of oxygen, which produces syngas, which is a renewable energy that we can use, as well as biochar and bio-oil. We can gasify, we can just combust it, we can incinerate it. So again, when we think about incineration, it's a direct burn. We're not controlling what's coming out. We're not producing renewable energy. Here, we're controlling what comes out, and we have a biochar product that can be used on the fields coming from that process. Next slide. So the biochar has shown it can absorb some of these extra nutrients. And again, we do a lot of work to try to understand the fertility of this biochar that comes from thermochemical processing, from pyrolysis and gasification. There's a very controlled burn that doesn't have the exhaust of just burning it. Next slide. And so injection, this is a manure injector. So again, that would just mean we're just putting it into the surface. So we're putting it down below the surface. We're literally chiseling, injecting. We can do it with manure. We can also do it with DAF. Next slide, sorry. And I have no more time, so I am going to end. Yeah, 2 more slides. That's okay. So we did an animal waste technology evaluation. There are, as you go out, you'll see there's some USB drives you can do, but you can also go to our website, just UMD AFTF, or you can do the QR code. And basically, one of these was looking at all the DAF in the state. Where is it? Where is it going? We looked at all the manure sources. We looked at all the nutrients, and we looked at all the different animal technologies and how they might address all of these different nutrients that we have in the state. And so we did interviews, focus groups, and we really looked at it through an environmental justice perspective, thinking about if you have a technology that reduces odor, how does that affect it? If you have something that increases traffic, how does that affect it? If you have something that decreases the pollutants, how might that affect it? So really looking at it through these technologies through that lens. Next slide. And so just I'm not going to go through the whole report. I don't have time. But just one last slide just to kind of show these technologies. So this is the baseline for if we have the manure resources that we have here in the state, how much greenhouse gases we're producing from just having this manure in the state. Okay. And so manure and DAF in the state. If we compost it, we reduce it from here down to here. So again, we do get more than 50% reductions by composting all of this waste that we have in the state. If we digest it, because we not only reduce all of the emissions, but we get renewable energy out of it, we actually get negative emissions. And thermochemical processing is also right here, just you can't really see it. It's right in line with the composting, actually. So we get pretty good reductions. So that's just kind of showing you one of the environmental advantages of doing some of these technologies with the waste resources that we have in the state. And I will end it there and put it on to Mr. Castley. Thank you very much.
I think I'm good.
Mr. Castley, could you give us a little bit of an overview of the anaerobic digestion specifically, and also the feasibility of anaerobic digestion on a large scale?
And thanks again for allowing me to come this evening. And I think you mentioned in your opening dialogue, Bioenergy Devco, the company that I work for, they opened their first anaerobic digester in the United States in Jessup, Maryland, right on the Maryland Food Center Authority. But that's just the first in the United States, partnering with their sister company, BTS Biogas in Italy. They have over 250 plants in multiple countries with over 25 years of experience in the industry. They have 29 international patents that will allow them to develop, design, engineer, and operate not only digesters for rural settings, but also urban settings. So for example, the digester that we have in Jessup, Maryland, it's located on a little over 5 acres. And as I said, it's right in the middle of the Food Center Authority where there's a lot of food processors. So it shortens the trip from the food, the waste that comes from the processor comes directly to our facility. And as Dr. Lansing explained the technology, we take in that food waste and we have 3 outputs. We extract the water for potential beneficial reuse. We capture the methane, which is a very flexible renewable energy source. It can be used to generate electricity for homes. It can be used to generate thermal heat for industry. It can be used for transportation for trucks or fleet vehicles. It can even be turned into what's called green hydrogen, which is kind of the next generation of renewable energy that we're just starting to tap into and look into. And I believe Delaware was just recently identified as a hydrogen hub. The third product, the third remaining piece, is classified as a soil amendment. It's a dark, rich, organic material. It looks a lot like compost, but it's a very stable material that we use for agricultural soil amendments on fields. Now, we're really happy to announce that after over 2 years of review and the exhaustive process, we were granted permits to construct our facility in Delaware, which is going to be an urban model in Seaford. And it's located right on the former Purdue compost facility. So we're going from 5 acres to over 100 acres. It's a much more conducive facility. It allows us to do more in one location. But that facility will essentially operate the same way. It will process largely just DAF material because that's the largest concentrate of organic waste that's in the region, but it'll go through the exact same process. I think the question was, like, how does AD impact the existing agricultural waste process, if you will? If you incorporate AD as one of the tools in processing DAF, there's several advantages. The first advantage would be basically a vessel to vessel transfer, meaning the materials leaving the processing center in a tanker truck. It's arriving to our facility and it's being pumped directly from that tanker truck into a vessel. So there's no air storage, so we can eliminate that issue of odor to the surrounding community. The second advantage would be, because it's a vessel-to-vessel transfer, we're also eliminating a potential food source for flies and other pests and things like that. So by denying that food source, obviously it gives us a much greater ability to control flies in the region. The third advantage would be by removing the water, the remaining material, the soil amendment, is it's far lighter than has the water in it, so it makes it much more economically profitable to transport, as whether you're transporting it to a local farm or whether you're transporting it out of the region. And because it's a solid material rather than a liquid land application, it has the ability to, they found that when you add it to the soil, it has the ability to decompact the soil, allowing the soil to retain more water. But it also, because it's solid and not a liquid, it has the ability to retain the nutrients much better during periods of heavy rains, where you could get potential runoff into streams and things like that. And probably the last advantage would be the anaerobic digestion process cooks off any of the potential harmful pathogens that are in the DAF material. So the remaining product, the soil amendment, is eliminated of that material. So we're super excited to be in the area, but we realize we're just one tool in the technology toolbox for use for this to address the environmental issues, but we're happy to be part of the solution. Thank you.
Thank you, Mr. Casserly. And our last panelist, Dr. Cummings, you are at the cutting edge of research when it comes to DAF. Could you give us a quick synopsis of the current research that's happening in your lab that is associated with DAF?
So we are not working with DAF. So I actually work upstream of all these processes. We work on sustainable feedstock production to sustain anaerobic digestion under various conditions. So for example, going into a DAF digester, it's my understanding that what we're working for is the microbes in these systems are actually carbon limited. There's so many nutrients in the waste that are coming out, the blood. In our case, we're working with chicken litter. There's so much nitrogen and phosphorus in that the microbes can't even digest it because it's just not enough basic carbon, which is the sugars that they do to fuel their metabolism. And so by adding lower quality carbon, lower quality plant material, which is higher carbon, we can actually improve the overall efficiency of the anaerobic digestion process and therefore get more biogas out of it and do a better job processing the minerals in it. And so that's what we're looking at now. We're looking at trying to turn crops that we have on the Delmarva on a regular basis, both cover crops from winter and also growing sustainable switchgrass, which is a perennial on farms, to use these as a source of carbon to sustain the anaerobic digestion process. And these guys did a great introduction for the process of AD, and certainly the amendment process, because what comes out of our AD process is a very rich, we call it element soil with the group we're working with, which is Chesapeake Utilities. And that is a great soil amendment to a farmer's field. The nutrients in it tend to be organic and well bound, and so even in a rainstorm, they're not going anywhere. They're not going to leach out as easily, and so it's better actually than putting down typically what you put on like inorganic fertilizer. And so if we put that carbon back on the field, we're doing a couple things. One is we are adding nutrients that are stable. We are adding carbon that's part of the mix of the digestate, and that carbon actually improves the structure of the soil, as Andrew mentioned. And then also, it also is a source where we actually start storing soil carbon. So carbon in the atmosphere, we're trying to cut out, reduce as much CO2 going into the atmosphere as can, but also the methane, which is even way more potent than CO2 in the atmosphere as a greenhouse gas. And so by storing carbon in the soil, that's on Earth, most carbon is stored in the soils. The largest pool of carbon is in the soils. And humans in general, through their activities, through agriculture, where we're tilling on a regular basis, we're disturbing that, and we're releasing a lot of carbon back into the soil, into the atmosphere, sorry, which is also fueling global climate change. And so by going to a system where we have feedstocks that are perennials, that are deep-rooted, and by using element soil and other digestates onto the landscape, we're actually putting that carbon back to the soil, into the soil where it can be stored and taken out of the atmospheric loop. So that's sort of an overview of our side of it. And with using an organism like switchgrass, it's a perennial. It's low input because the last thing you want to do in the equation is when you're trying to produce feedstocks to optimize your anaerobic digestion, you don't want to have high carbon input. You don't want to have to use fertilizers on them. You want to do everything you can to make the plants, make the biology do what biology does best. And if these plants are really good at extracting nutrients out of the soil and extracting water, and we have a large stock of genetic resources that we can call upon to actually tailor certain plants to certain sites. So if where we have salinity and seawater inundation, for example, we can get salt resistant varieties to produce on those soils where farmers may have lost their ability to produce other crops. And so the goal here is that by going to these, we're trying to actually commodify, the goal of our big project is to commodify this, to create a whole new agricultural ecosystem in which we are producing feedstocks to help build anaerobic digestion systems and optimize their function, thereby treating the vast amounts of poultry litter that are produced in the region, do it effectively, make biomass that can go out to be used at the farm level or at community level, and at the same time reduce the nutrients that are being put onto the landscape. So altogether, it's sort of a win-win, and these systems, as you mentioned, they're used in Europe all over the place. I mean, my first exposure to this was at a panel like this, and there was a gentleman from Italy, and he went through this whole system, how it was designed, and everything stayed on site, and everything there powered his farm and the neighbors' houses, and it was quite impressive to see that we can actually generate a very good circular bioeconomy where we keep our waste and utilize our waste to the benefit of the entire community.
Thank you, Dr. Cumming. I have one very broad question for all of our panelists, and I think that's all the time that we'll have. So this big, broad question, if each of you could take some time to answer parts of it that apply to your work, that would be awesome. So we discussed some of the alternative technologies that are available. One of the biggest concern is, should we be worried about the impact on the air, let's say for example, particulates when it comes to the combustion with methane, what impact will that have? Looking at some of our water quality issues, do you think there will be any impacts to our local water bodies with any of these technologies that were described? So that is a very, very broad topic. So if you could elaborate a little bit on some of the land, water, air impacts.
So we'll start. So land, water, air. We'll start with air. In terms of air, when we think about anaerobic digestion, basically, first you have to think about what you're starting with. So if you're starting with dairy manure, you're starting with DAF, you have air emissions coming up from that substance, you have odors, and you have methane coming up from that. By covering that, which we do in a digester, we're capturing that. And then we can, you can just flare it. And that flare is, again, taking greenhouse gases, methane, that's really powerful, and putting it back to CO2, which is the same CO2 that was from the plants that the cow ate, the cow pooped out, or the chicken, and then that's part of that cycle. So really, when we're doing that, we're reducing emissions that would occur, odors and methane that would go into the atmosphere. We're taking that and we're reducing those odors. And when we're combusting, it combusts to CO2, but that's the same carbon cycle. It's not additional CO2. And we've done a lot of air emissions work on digesters, looking at what are the emissions coming out. And the reality is they reduce emissions coming out. So we've published lots of peer-reviewed papers on the reductions in emissions, reductions in greenhouse gases. So this isn't something that adds air emissions. When you get to composting, again, we shouldn't have odors. If we have odors, it's because we're not managing our compost properly. Okay, so we shouldn't, and the CO2 that comes out of the compost pile is, again, the same CO2 of the plant material that came in. So it's not additionality. When we go to the thermochemical processing, it's really how are you managing that? So you saw there's kind of a continuum, right? So if we're just burning it, we're going to have air emissions. If we actually limit the oxygen and do it at a very high temperature, it's actually very efficient, then we're not producing CO2. We're actually producing we're actually producing CO and hydrogen. And that is actually can be used as a renewable energy source. And so it depends. And then you get biochar. But if you're just burning it, you get ash. I mean, it's just ash. This isn't biochar. So biochar is like a really carbonaceous kind of material. It's not ash because it's at such a high controlled process that a lot of that carbon comes contained in that biochar. So it's really about how are you managing these things for air emissions. And when we think about the water, so when we do a digestion process, we actually turn it all to ammonia. And that's good because when we put ammonia on the soil is negatively charged. And so the ammonia actually sticks to the soil versus if we were to put something like, chemical fertilizer on, that nitrates can actually, they're also negative. So it likes to go down to groundwater. That doesn't happen when we've done a digestion process. It stays right there. It sticks to the soil. And so it's actually a really great way of preserving water resources. And then they spoke a little bit about the land. If you put compost, if you put biochar, or you put digestate on, it actually builds up the soil and it can actually help sequester more carbon in that soil by providing that great carbon and nutrients in the soil surface that it needs versus putting chemical fertilizer in. So when we go back to the word DAF, DAF is a fertilizer that we're putting in that has, it is a fertilizer that we're substituting chemical fertilizer for. We just want to process it or do other things so that we don't have the odors associated with it. So you can inject it, you can digest it, compost, etc.
I think that the important thing to look at here is that that's a resource that we have here on the Delmarva. We don't have to import it from Ukraine. We don't have to use the Haber process to fix nitrogen out of the atmosphere, which is amazingly energy reliant. We can use it here and produce it here, and then we can even export it. So certainly with our high phosphorus digestates coming out, I don't see any reason why we can't export that from the Delmarva, because phosphorus, we only have maybe 80 years of rock phosphorus left on the planet for farming, although they just find a big new store of phosphorus, mineral phosphorus in Sweden, I believe. And most of the phosphorus is in Morocco, and the Chinese are buying most of that. And so it's really at this point becoming a resource that we need to keep and as a resource for the United States in order to sustain agricultural production. So if we look at this waste as a resource and change the economy around that, we again get to the point where we have a circular economy, that we have the plants on the ground, the animals, the waste goes, we have the food from that, we have the waste that goes around a big circle, and then we start all over again using the energy that we build to sustain communities and the farms themselves, and also then to enrich the soil so that we can continue to produce plants and continue the cycle as it goes.
So, can you hear me? So Dr. Lansing stole all the technical stuff that I was going to tell you. But I will just summarize on his paper. When we talk about a circular economy, essentially there's this perception that we are generating a whole new material. what you need to understand is we're taking an environmental liability and turning it into an economic asset. So it's not like this material already exists. The way that we're processing it is not sustainable. We're just proposing that we process it in a different way that's more environmentally responsible and more economically feasible.
Thank you very much.
Thank you.